We're going to look at a very simplistic model of growth and decay to start off with, and then we'll look at a little bit more involved one. Okay. It just works off a basic idea that growth and decay is always proportional to the population. And the more people you have, more people are going to be born, more people are going to die. Well, it only stands to reason, doesn't it? So if that's true, if we're saying it's directly proportional, then the P to T, the rate of change of population, must be equal to some constant times the population. That's it. It's a very simplistic model. So if I turn it upside down, because I want it with respect to P, that's my variable, the population, then to T to P will be 1 on KP. So T would be 1 on K times the integral of to P on P. Well, integrate 1 on P with respect to P, and we get log P. So KT equals log P plus a constant. Notice I didn't write it as KC, because a constant times a constant is still a constant number. So log P would be KT minus C. Exponentialise both sides. We now have a formula for population, e to the KT minus C, but I'm going to write that a bit differently because, of course, e to the power of minus C, using our log laws, I can break that off. And again, that's just going to be a constant number. Now, of course, they've sucked all the life out of this topic because it's meant to be a wonderful demonstration of an application of calculus, but now they say, well, if you've got this differential equation to P to T equals KP, you can just quote the answer, P equals AE to KT. So how to do an application of calculus without using any calculus? By the way, there is another solution to this, which would be trivial, of course. What would it be? There's another possibility, another answer for this. A solution to P to T is equal to KP. P equals 0. It's a trivial solution, but that's why we don't consider it. Because obviously if you had no population, then it's not going to grow, it's not going to decay, so the rate of change would be 0 as well. Trivial solution. Solution we're interested in is this one, AE to the KT. P is the population at any particular time. A would end up being the initial population if you think about it. Because if you were to sub in T equals 0, then e to the power of 0 is 1. So you get A. And K is our growth or decay constant, depending on whether increasing or decreasing. T, of course, is time. So let's have a look at a question. Growth rate per hour of bacteria. So right now, let's assume you have 1 million gooby-wops crawling all over you. Now, you can't see them, they're bacteria, but trust me, they're all over you. Oh yeah, bacteria loves it. You can't see them, they're just crawling all over you. And you've got 1 million of them at the moment. A typical sort of question they might ask, because we're not going to use the calculus, they might say, well, okay, go and show this as a solution. Now, they're not expecting you to do what I just did, work backwards. I'm still going to use calculus, mind you. I'm going to say, well, hang on. If P equals AE to the 0.1 T, if I differentiate that, I get 0.1 AE to the 0.1 T. But hang on, I just said P was AE to the 0.1 T. Oh, look, I've ended up with the P to T is equal to some constant times P. So it is a solution to our differential equation of the P to T is equal to, well, in this case, 0.1 is the constant. I suppose that's an advantage of a show that question. Show that means just show it works. All right, well, let's see those million bacteria, how busy they are. After 3.5 hours, how much bacteria have you got on your... initial population was 1 million. I mean, I suppose you could formally work it out when T equals 0, P is 1 million, so therefore A is 1 million. So P is 1 million E to the 0.1 T. We want to know when T is 3.5. Sub that in, we now have 1,419,000. It's almost 50% more already. Bacteria too. All right, let's do another one. We're now going to do a decay one, because you see, on this island, there's only 1,732 people on this island in 1960, but clearly they don't get along, because in 1970 the population's now 1,260. Find the annual growth rate. Well, actually turns out to be a decay rate, of course, assuming it's proportional to population. So, okay, we can assume P to T is equal to some constant times P. And we know the solution to that magically becomes P equals AE to the KT. They've told me the initial population, so formally I could work it out. When T equals 0, P turns out to be 1732, so therefore A is 1732. So I have 1732 e to the KT. But they've also told me that after 10 years, the population is now 1,260. So we just got this exponential equation to solve. 1,260 is 1,732 e to the 10k. So e to the 10k is this wonderful fraction. To undo the exponential, we log. So we get 10k is the log of that fraction. I mean, yes, it does simplify down, but I'm not going to bother simplifying it down. So k is 1/10 the log of 12601732. They've set to the nearest percent, so bung it in the calculator, and we get negative 0.031865, etc., etc., etc. So to the nearest percent, they're decaying at -3%. So in how many years will the population be halved? So half that of 1960. Well, in fact, it doesn't really matter what year I start with, because of course the way growth and decay works is at any starting point, it's still going to take the same number of years to halve that particular population. It's what's known as a half-life. You might have heard of that in science. Same idea. So P is 866. We may as well, because they've specifically said half of that in 1960. So when's P 866? We end up with e to the KT equals a half, and that's why, as I say, you could pick any point in time because it's always going to cancel down to be a half. 1 on K log a half, which basically is, again, going to your science, you might recognise it's a very simple formula, but there's your formula for half-life. If you know what the decay rate is, 1 on K log of a half. 21.786, this one turns out to be, when we sub in our K. Notice I left it just as K. I didn't write the value of K from all that. I mean, I store that in my calculator, but no point writing it. It just takes time, so I'll leave it as K. So in 22 years, the population has halved. Now, you got to think about these questions, because say the answer had turned out to be 21.2. And the question says, in how many years will the population be half that? You still round up, because at 21 years, it hasn't halved yet. Just be careful with that sort of idea. Mind you, having said that, it'll be a harsh person who penalised you. If you got your 21 point whatever, I mean, that's probably good enough. All right, so that's a very basic model. It's a model that I guess Toon look at. Oh, we'll just do a handful of those ones.